Welcome to all. Today we will start from the previous questions that we gave as an practice question. Okay. So, we will go through the question and try to solve it, and you can match with your given answers. So, we looked into question 4. The question 4 ran as such. A vehicle bumper absorbs energy during a crash, okay, and the properties of the vehicles is given. So, the vehicle kinetic energy is 15 kilojoule. The bumper has two plastic hinges, okay, and the plastic moment of each hinge is 120 kilonewton meter, and the total rotation per hinge is 0.06 radians. Okay. So, the given question was asked how much energy do the hinges absorb and what happens to the remaining energy. Okay. So, as we discussed earlier, okay, the physical interpretation of the plastic hinges. Okay. So, normally what we have learned for a plastic hinge is like this. Okay. So, for any given structure, okay, if there is a discontinuity here and a moment is allowed, okay, so the moment resisting capacity at this point is 0. Okay. So, this we can assume it as a simple junction, okay, with a bolt running through and through. Okay. So, this criteria was called as a plastic hinge. In case of our continuous structures like a beam or a column, okay, made up of reinforced concrete or any metallic materials, the plastic hinge definition is as such. Okay. So, when the system goes under bending, okay, if you look into the cross section profile, okay, if you look into the cross section, so there will be a neutral axis, okay, which neither elongates nor contracts. Okay. And if the bending is as such, okay, the top portion will go under compression and the bottom portion will go under tension. Okay. If we keep on increasing the load, okay, if this is the load F and if we keep on increasing the load, the strain profile keeps on increasing. Okay. So, the neutral axis is maintained. Okay. So, strain keeps on increasing till it reaches the elastic strain. Okay. So, till the elastic strain is reached. Okay. So, here it has reached the elastic strain. Okay. After reaching the elastic strain, the plastic deformation begins to occur. Okay. So, the plastic deformation now propagates back to the other layers, okay, the layer beneath the extreme layers. So, this keeps on increasing. Okay. So, this keeps on propagating in the system. Okay. So, propagation keeps on increasing. Okay. So, there comes a condition where the entire cross section has gone under plastic deformation. Okay. So, this condition is treated as the formation of the plastic hinge. Okay. And the moment required to get the section into this condition is called the plastic moment. Okay. So, this is called the plastic moment capacity. Okay. The moment required to get the section into the full plastic regime. Okay. So, this is that particular number. Okay. So, in this question it is asked that given the configuration, how much energy does the hinges absorb and what happens to the remaining energy. Okay. I hope you have done this question and let us look into the solution. Okay. So, as we have seen earlier, okay, the total energy absorbed by the hinges is given by the summation of the plastic moment capacity multiplied by the rotations. Okay. So, here two hinges can form. Okay. So, the summation will be over two hinges, okay, hinge 1 plus hinge 2. The capacity is the moment capacity is same for both the hinges. So, it is 120 times 120, okay, and the rotation is 0.06 in both the cases. Okay. So, this becomes the total moment, total energy absorbed by the hinges, okay, which is around 14.4 kilojoules. Okay. So, the initial kinetic energy was 15 kilojoule. Okay. So, the initial kinetic energy was 15 kilojoule, okay, and out of 15 kilojoule 14.4 kilojoule was absorbed by the hinges. Okay. So, the remaining energy is 0.6 kilojoule. Okay. So, what happens to that? So, the remaining kinetic energy may be absorbed by the elastic deformation and other structural component, or by friction, by heat generation, or any other mechanism. Okay. So, this portion goes into the bumper. Okay. Out of the available 15 kilojoules, this portion goes into the bumper, and the other remaining one is absorbed by the other mechanisms. Okay. Moving ahead. So, we look into the next question. So, in this question we are asked to design a simple energy absorber for a 10 kilojoule impact. Okay. So, the total impact energy given is 10 kilojoule. Okay. So, the requirements is that we can use 3 identical plastic hinges. So, in this system 3 plastic hinges can form. Okay. Okay. So, in this mechanism we are allowed to have 3 plastic hinges. So, the each hinge rotation is 0.05 radians. Okay. So, this is 0.05, 0.05, 0.05 radians. Okay. And the given criteria is that it should absorb all 10 kilojoule of energy. Okay. So, now we have to design this hinge. Okay. And in order to design this hinge, we need to know how much is the plastic moment needed for each particular hinge. Okay. So, the total required energy is, the demand is 10 kilojoule. Okay. 3 identical hinges are there. Okay. Okay. So, 3 identical hinges are there. Okay. Each hinge theta is 0.05 and MP is same for all hinges. Okay. So, we know that total energy, total 10 kilojoule has to be absorbed by the all the 3 hinges. Okay. So, 10 kilojoule. Okay. MP is same for each of the 3 cases. Okay. So, theta 1 plus theta 2 plus theta 3. Okay. And all these 3 quantities are same, 0.05 radians. Okay. So, this becomes 0.05 radians. Okay. So, now we can get MP 0.05 plus 0.05 plus 0.05 equals to 10 kilojoule. Okay. So, MP times 0.15 equals to 10 kilojoule. Okay. So, MP is given by 66.67 Newton meter. Okay. So, in this way we can design our hinges. Okay. So, each hinge has a plastic moment capacity of 66.67 kilonewton meter. Okay. So, now moving ahead to the next question. So, the problem statement is given as carbon epoxy composite structure. Okay. So, this is a carbon epoxy based composite structure. Okay. So, this might be a layered structure, okay, which is made up of carbon fibers and sandwiched epoxy layers. Okay. So, this is a composite layer. Okay. So, this is being designed for an automotive crashworthiness application. Okay. So, its application is during a vehicle impact. Okay. So, this layer will somehow protect either the occupant or it will protect the cargo in a given crash scenario. Okay. So, based on the experimental data from the crash test, the following specific energy absorption values were obtained. Okay. So, for this structure, okay, the specific energy absorption is nothing but the total energy absorbed per unit mass. Okay. So, number of plies. Okay. So, these are called the plies. Okay. If I made this composite layer, okay, so it is a layered structure. Okay. So, this thin layers are called plies. Okay. So, if I have a configuration of 8 plies, okay, say my structure contains this type of sandwiched 8 plies, okay, then the specific energy absorbed is 32.14, 12 plies 32.19 and 16 plies 32.2. Okay. Here we can see that even if we increase the number of plies, there is no significant increase in the specific energy. Okay. So, this way also we can optimize our number of plies. Okay. So, using this given information, okay, the composite density is 1.6 grams per cubic meter and the crushing distance is 50 mm 50 mm and the cross sectional area is 25 centimeter square. Fiber orientation is 090 layer. Okay. It means that the first layer will be oriented in this fashion, means that the first layer, if the orientation of first layer is this way, okay, the other layer will be oriented 90 degrees to this layer. Okay. So, the other layer orientation will be 90 degree. Okay. So, this way the layer will be sandwiched, okay, again 0 degree and 90 degree, 0 degree, 90 degree. So, this way this 8 layers, 12 layers or 16 plies layers will be arranged. Okay. So, here we will do some basic calculations. We will calculate the total energy absorbed by a 16 ply composite specimen during complete crushing. Okay. It means that the complete crushing will occur, and we will also try to find the average crushing force during the energy absorption process. Okay. We will also try to calculate the total energy absorbed during this particular process. Okay. So, for a 16 ply configuration, okay, we will calculate the total volume first. Okay. So, area into the crushing distance. Okay. So, as we have seen earlier, okay, the crushing distance is 15 mm and the cross sectional area is 25 centimeter square. So, the cross sectional area is 25 centimeter square, okay, and this is allowed to crush to a total extent of 50 mm. Okay. So, when the impact occurs, this entire configuration will crush to 50 mm. Okay. So, the total volume of this mechanism is cross sectional area times the crushing distance. Okay. So, the crushed volume is 25 centimeters square, that was the cross sectional area, times the crushing distance. Okay. So, it comes around to 125 centimeters square. Okay. The mass, the density is given, so we multiply by the volume, so we get the total mass. Okay. So, the energy absorbed for a 16 ply is specific energy per unit mass multiplied by the mass. Okay. So, the specific energy for a 16 mm configuration was given as 32.2. Okay. So, this is the specific energy. Okay. So, the specific energy per unit mass. Okay. So, the total energy absorbed per unit mass. Okay. So, what we did was we calculated the total volume, okay, that is required in order to achieve the total impact, okay, and we calculated the corresponding mass of the system, and from there we can calculate the total energy that will be absorbed by this given system. Okay. So, we calculated the volume, from volume we calculated the mass, and from the mass multiplying with the specific energy we calculated the total energy absorbed by this 16 ply configuration. Okay. So, what is the average crushing force? Average crushing force is the energy per unit distance. Okay. So, this is the average crushing force, okay, that is applied on this particular system. Okay. So, let us say we have been given to do the same thing for a 8 ply configuration. Okay. So, what will change here? So, the volume of the system remains same. 8 ply configuration also has a cross sectional area of 25 centimeters square. Okay. So, the cross sectional area is same. Okay. It might change also for other given configuration, and the crushing distance is same. Okay. So, we will use the corresponding value, okay, area for a 8 ply configuration, 8 ply area multiplied by the crushing distance of 8 ply. Okay. So, this will gives us the volume for 8 ply. Okay. From there we will multiply with the density of the 8 ply composite. So, for 8 ply composite we will multiply with the density and we will get the mass of the 8 ply configuration, and mass of the 8 ply configuration will multiply with the specific energy for the 8 ply. Okay. So, this multiplied by the mass of 8 ply configuration, okay, will gives us the total energy absorbed by this 8 ply configuration. Okay. So, for the 12 ply configuration again the same thing has to be repeated. Okay. So, volume of 12 ply will be given by area of 12 ply configuration times the total crushing distance of the 12 ply configuration. Okay. Then total mass of the 12 ply configuration will be density of the 12 ply configuration multiplied by the volume of 12 ply configuration, and total energy will be given by the specific energy of the 12 ply configuration multiplied by the mass of the 12 ply configuration. Okay. So, in this way for the given systems we can calculate the total energy. Okay. And the average force will be total energy divided by the crushing distance of that particular configuration. Okay. So, this way we showed for the 12 ply configuration, and the same thing can be done for the 16 ply configuration. It is shown, same thing can be done for the 12 ply configuration and the 8 ply configuration. So, moving ahead. So, in this case a scenario is given. So, if the structure needs to absorb 500 joules of impact energy, what minimum volume of composite material is required? Okay. So, our demand is given. Okay. So, the demand is 500 joules. Okay. Here we have seen the energy absorption for the 16 ply configuration is 6440 joules. Okay. So, 16 ply can, if it is fully impacted, it can absorb 6400 joules. Okay. Now, we are asked to absorb 500 joules of impact energy. So, what is the minimum volume of the composite materials is required, and after that we have to compare the energy absorption efficiency between 8 ply and 16 ply configuration. Okay. So, we will look into this. So, minimum volume for a 500 joule. Okay. So, the required mass is, if we take a 16 ply configuration, okay, if we take a 16 ply configuration, then we required around 15 grams of the mass for absorbing this much. So, if 16 ply is used, okay, so 16 ply has a configuration of 25 centimeter square, and the total crushing distance is 50 mm. Okay. So, if the entire thing is crushed, okay, if the entire thing is used, it can absorb an energy of 6440 joules. Okay. Now, the total energy demand is only 500 joules. Okay. So, in order to absorb 6400 joules, okay, the total mass requirement was 200 grams. Okay. So, here if 6440 joules has to be absorbed, then 200 grams of 16 ply configuration is required. Okay. But we now need to absorb only 500 joules. Okay. So, for that only 15.53 grams is required. Okay. We are calculating in the reverse order. So, the required volume, okay, is mass divided by the density. So, 9.71 centimeter cubic of this configuration is required. Okay. So, if 6400 joules was required, then 200 grams and correspondingly 125 centimeter cubic volume of material was required, okay, for a 16 ply configuration. Okay. Here the requirement is only 500 joules. Okay. So, for 500 joules 15.53 gram is required, and correspondingly 9.71 cubic centimeter is required. Okay. So, we can see that as the energy demand is less compared to the maximum capacity of the 16 ply configuration, then the material requirement is also less. Okay. So, efficiency comparison between a 8 ply configuration, 16 ply configuration is that. So, as we have pointed out earlier, okay, when we started this particular problem, here we can see that the specific energy absorption, okay, between this 3 ply configuration is not very much. Okay. So, if 8 plies are used, then 32.14 is there, 12 plies 32.19 and 16 plies 32.20. Okay. So, from here to here if we move, the total energy absorbed is only 0.05 joules. Okay. And from, if we compare with the first one, okay, then 0.06 joules. Okay. So, the energy increase due to this changing ply configuration is not very much. Okay. So, this way even if we use an 8-ply configuration, okay, we can very efficiently use our materials because we are not gaining much by using more number of plies. Okay. Had this been numbered like 32, 40, 60, okay, then we can see that there is a significant increase in the specific energy absorption, but here increase in the energy absorption is minimal. Okay. So, the same thing has been pointed out here. Okay. So, the difference is only 0.19% increase. Okay. So, this is a minimal improvement with the thickness. Okay. So, we are not gaining much by increasing higher number of plies. Okay. So, moving ahead, okay, next application. So, based on the research finding, explain why the SEA values remain relatively constant despite increasing ply count. Okay. And suggest how changing the fiber orientation from 090 to plus minus 45 degree might affect the energy absorption based on the failure modes described. Okay. So, for this thing small literature review is required. Okay. So, I encourage you to do the literature review. Some explanations has been provided here, you can improve on that and add your own findings also. Okay. So, we will discuss some of the key findings, okay, and later on you can work on that and add your own findings also. Okay. So, constant SEA energy absorptions, okay, why the SEA energy, the specific energy per unit mass is not increasing by much. So, the energy absorption is primarily governed by the fiber failure mechanisms rather than the total thickness. Okay. So, the energy absorption is a function of the fiber failure mechanism. Okay. So, here what is happening is that there is a stabilized crushing region, okay, and it maintains consistent energy dissipation per unit mass. Okay. So, in this all this configuration there is a stabilized crushing region. Okay. So, due to this stabilized crushing region, even if we add more mass, okay, this is not going to affect my total energy absorptions. Okay. So, thereby adding more number of plies does not change the fundamental failure mode. Okay. So, what is happening here is that in this configuration, okay, there is a fundamental failure mode established, okay, and it saturates, okay, and forms a stable crushing region. Okay. So, even if we keep on adding more and more number of plies, that other plies are not engaging there to absorb more energies. Okay. So, the top layers and all the layers beneath it are already failing. Okay. So, the system is suffering from a failure mechanism, okay, which is stabilized at this crushing region. Okay. So, what will be the effect of the here? So, this is a small explanation of the unit, okay, of this thing. You can add your more in explanations, you can improve on this explanations and write it in more details. Okay. So, this thing you can treat as your homework where you can look into the literature and go into much more depth and detail and explain the failure mechanism also. So, this fiber failure mechanism can be treated as a homework also. Okay. Next comes the fiber orientation effect. Okay. It has been asked that the presently used material had a fiber configuration of 090. So, what will happen if we use a plus minus 45 degree orientation? Okay. Basically, what is being asked is that this fiber, okay, so they are placed, one fiber is placed like this, okay, a 0 configuration, and the other fiber is oriented 90 degrees. So, the next layer beneath layer is oriented, okay. So, this layer is oriented 90 degrees, okay, corresponding to this layer, okay, and this way they are being stacked. Okay. So, it is being asked that if we stack it on a plus minus 45 degree orientation, okay, first layer is plus 45, second layer is minus 45. Okay. So, if we stack this thing, what will be the effect? Okay. So, intuitively we can say that this orientation would likely increase the absorption. Okay. So, why? This will happen because more fiber breakage will be there. Okay. So, more number of fibers will be engaged during this crushing process. Okay. So, this microfracturing process will be engaging more and more number of layers. Okay. So, this will increase the fracture toughness with increasing fiber angle. So, as the fiber angle increases, the fracture toughness and the more number of fibers will be increased. Okay. So, it is intuitively inferred that using a different orientation configuration will increase the crushing capacity of the entire system. So, again this thing can again be looked into detail, okay, and a proper explanation of the things can be prepared and submitted. Okay. So, these things we can find in the different literature reviews, and in depth detailed explanation can be obtained. Okay. So, here the main point is that if we try to increase the more number of plies, okay, in a given configuration, there might be cases where the specific energy does not increases. Okay. This will be due to the reason that during a given orientation, okay, and a given configuration, the crushing region is almost fixed. Okay. Even if we increase the more number of layer, this crushing region does not engage the other increased layers. Okay. So, that is why the efficiency does not increases. Okay. So, a good way to use more number of piles will be orienting the fibers in different angles. Okay. So, what will happen is that this will try to engage the bottom layers also. Okay. So, the crushing region will increase. Okay. So, this will try to effectively increase the efficiency of the absorption capacity. Okay. So, this way the things can be optimized. Okay. So, moving ahead. Okay. So, we will look into now the fiber dosage calculations. Okay. So, here it is asked to design a hybrid fiber mix for 40% energy absorption increase. Okay. So, the energy absorption increase, target energy absorption increase is 40%. Okay. So, we have to design the fiber mix. Okay. So, the data is given that the plain concrete absorption is 2.5 kilojoule per meter square. Okay. So, if we take a plain concrete sample, okay, so the energy absorption is 2.5 kilojoule for a unit area. Okay. Steel fibers, the dosage is around 0.8% per kg per cubic meter. Okay. And polypropylene is around 0.3% per kg per cubic meter. Okay. So, the target absorption is 2.5 is absorbed by the concrete. Okay. So, we need a 40% increase. So, the target absorption is 3.5 kilojoule per cubic meter from this hybrid fiber mix. Hybrid fiber mix means in concrete we will add some sort of fibers. Okay. Either they can be steel fibers or they can be polypropylene fibers. Okay. So, using 40 kgs of steel fibers, that is plus 32% and 27 kg of polypropylene, okay, plus 8%. Okay. So, here we will calculate the target absorption. Target absorption is given was plain concrete can absorb 2.5. So, 3.5 is required. So, the required enhancement is around 1 kilojoule per cubic meter. Okay. So, from 25 we are going to 3.5. Okay. So, enhancement required is 1 kilojoule. So, using 40 kg per cubic meter of steel fiber and 27 kg per cubic meter of polypropylene fiber. So, the total energy absorption is this much, required enhancement is this much. So, here if we use this particular configuration, we will get the required enhancement of 1 kg. Okay. So, here we come to a conclusion of this chapter of designing the energy absorption materials. Okay. So, in this chapter what we have done is that we have looked into different types of energy absorption materials, we looked into their properties, we looked into how to optimize them, we looked into how to design them, we looked into their detailed mechanism for various cases. Okay. And after that we tried to do some design also, where we took different cases and we tried to find out the mechanism, we tried to calculate the total energy absorbed, we tried to calculate the specific energy absorbed for different configurations. Okay. So, using this knowledge we can try and start designing our different absorption materials. Okay. So, the first thing that we look for any energy absorbing material is that we have to get a large plateau. Okay. Large plateau means that the total energy absorption of that particular material and of that configuration should be very large, so that a significant amount of energy is absorbed. So, we always look for a material exhibiting a large Plateau effect. Okay. So, once we have the material, then we will look into the optimizing the geometry, optimizing the configuration, optimizing the orientation of that particular material. Okay. As we have seen in the case of plies, using the same number of plies, but in a different orientation might increase the energy absorption capacity. Similarly, we have looked that using different geometries, okay, using different shapes can also increase the energy efficiency of the energy absorbing materials. After that, for a particular application, we have to look into the total energy demand, and using that total energy demand, we can calculate the different energy absorbent capacities. So, I hope this chapter will help in designing the total energy absorbing materials. Thank you.